here in the laboratory of nuclear physics at University, Shanghai Research Center for Theoretical Nuclear Physics, NLC. It's also sponsored by the program of distribution talents of displaying universities, the Journal of Nuclear Science and Technology, and it's an industry of social reform. So next I will introduce Professor Shohei Nishida. I know him very long time ago. Actually, it's at the beginning I started working in Bell. Because at that time I was a student. Once I find a problem trouble in Bell software, I always got help from Nishida. So it was always easy to fix all the problems. It's good for us to move forward on this analysis. But sometimes I didn't become an expert on software. So everything was so easy. And this some research is 50 in science physics from Kyoto University, Japan, in 2003 for the study of radiative meson decays into high gamma and the high gamma condensate. He then moved to KK, the high energy accelerator of hydrogen in Japan, and has been worked for Bell and Bell II experiment in years. He has developed the algorithm detector, the particle identification device in the forward indicator of the Bell II detector. Actually, he is the leader of this algorithm. He also started on radiative meson decays as well, and recently started working on lepton level evaluating metal decays in the darkmatter searches at Bell and Bell II. And he also served the physics coordinator at Bell experiment since 2016. So actually, Mr. Science and expert of physics, analysis, software, and also hardware. So I want to invite some presentation on the state of Bell experiment, darkmatter searching. So welcome.
Yeah, I'm very happy to be here in Fudan University. And yes, okay, now let me present or have a seminar on this status of Belle II and darkmatter search. Okay, that's maybe you already know, but this is the KEKB and high energy accelerator research organization. That's the official name, and we call KK. It's something from Japanese word. Which is in Tsukuba, and this is an institute for elementary particle physics, but also various researches for life or science matters with with accelerators. And we have another campus, Tokai Village, and J-Park accelerator. Tokai. Anyway, inside KK, we have this 3-kilometer accelerator. Now it's called SuperKEKB. But originally this was constructed as a part of Tristan accelerator. This was E plus E minus collider in 1980s, and at that time this was the highest energy machine in the world. But this experiment tried to find the top quarks, but unfortunately, even at the beginning of Tristan, it was found out that the top quark cannot discover this accelerator. But anyway, after that, this accelerator became KEKB for physics, and then now it's SuperKEKB. I don't need to explain, but in the standard model we have various imperfect theory, and we have but we don't know about dark matter. dark matter is not a part of the standard model, and we expect that there should be some new particles like SUSY or left quark or extra dimension. I don't know if you call it the same way in Chinese. This is Japanese. But anyway, so we are looking for new physics. And that's, of course, a part of Belle II experiment. And also, I mean, Belle II is a kind of flavor physics experiment. So flavor is a species of the quarks and leptons. And only with interaction changes the space. So so basically this, I mean, study of this various kind of quarks means it's a study of interaction, with interaction. And among these quarks with this charm bottom and top, relatively high, relatively large mass. Top, of course, is heaviest. But this does, I mean, this immediately decays. So what we can study with accelerator, I mean, with SuperKEKB, is charm, bottom, up. So these are called heavy flavor. And because this has really many kind of decay modes, we have a lot of things to study. And what in that sense, for students, maybe it's easier to write a paper for this study. But anyway, the purpose is, I mean, we want to do the precise measurement of these decays. And with this one, we can provide the information of the physics beyond the standard. So, you know, this many, you already know, we see this kind of loop diagram. So, this, when some particle decays through this loop diagram, then new physics particle can virtually contribute inside of this decays. And so we measure some observable, like branching fractions, asymmetry, and we compare with a standard model expectation. Then we will find, and if we have some discrepancy, we will find maybe. So that's what we want to do with this. So this is a general thing that we want to do with flavor. Okay, so then let me go to the two detector and the experiment. So you see, this we have 3 kilometer axis. This is SuperKEKB. So we have this line, linear accelerator. So we produce electrons and positrons here and accelerate to 4 GeV for positrons and 7 GeV for electrons, and then circulate inside this main SuperKEKB and collide at the Belle II. The circumference is 3 kilometers. And as I said, this was previously KKB accelerator, and at that time we had the Belle detector. And Belle experiment was conducted in between, I found this 1999 to 2010, and we still analyze the data at that time. The original purpose of Belle experiment is verification of Kobayashi. And okay, so finally this theory was verified by Belle and the Bavaro experiment in US. Then these two people got a Nobel Prize in 2008. This is Kobayashi-san. This is Pastas. Okay. And now we have Belle II experiment. This is the right hand side. This is a Belle II detector. So you can imagine the size of detector. This is something to me. And so detector is something like 8 meters times 8 meters. And inside this Belle II detector, we have several detectors, and most inner part we have vertex detector. And this is some pixel detector, which I got as data, and also SVD, silicon vertex detector. This is double-sided string detector. Anyway, we measure the position of decay, B decays, for example, at this vertex detector. Then outside we have the drift chamber. This is used to measure the momentum and also maybe dx. And outside we have time particle identification device and the top count and barrier and the areas. We have the reach which I work on and the forward. And okay, I will have calorimeter, and then most outside KLM. I think Fudan group as well. Okay, this is just it's a big international collaboration with 27 countries and regions, with 120 institutes and more than 1,000 researchers. Okay, students are also included. So you can compare with LHC. LHC has Atlas like 4,000 researchers, but that doesn't mean students. So it's much smaller than Atlas and CM, but still it's a big collaboration. And in 2016, we started operation without detector, just for commission sector. And after that, in 2018, we started operation with Belle II, but at that time, inner detector, vertex or SVD or Excel, not and from 2019, we have real operation with full Belle II detector, but it's not really full because the second layer of PXC detector was not installed. And now we are doing a kind of shutdown to install the second layer of detectors. That's what we are doing. And I have got this one a little bit late, but just a few more than the two experiments. So this is called B factory experiment because we produce a large number of EMS. So the interaction is E plus E minus. E plus E minus goes to position 4s, and position 4 is compared to BB bar. And we have 3 times more this continuum process. So this is E plus E minus QQ bar. This is 3 plus number. But okay, so in that sense, we produce a lot of charmless with this process. And E plus E minus tau plus tau minus is also important process. We produce a lot of tau vectors. So we can do detailed study of B or charm, B or other charmless on the surface or charm value and the tau. Okay, and this is how the event looks like in this article. Let me on there about the status. So you see, as I said, operation is full detector starting in 2019, and so we really want a lot of B mesons or other charm or tau properties. So luminosity is a kind of performance correction. So that's important. So and actually last year, just before the shutdown for LS1, we achieved 4.7 times 10 to 34 luminosity. And this is actually world record, twice of KK. But our target, our original target, something aiming 1 order higher than 35. Order something 6 times 35, 10 to 30. That's what we are aiming. By the way, when we use this, we get this one. Originally, we plan to take around until June to the end of June. So unfortunately, recently, this electricity, maybe not in China, but in Japan or in any other part of the world, electricity is very high. And we finally use basically all the budget. And suddenly, around 1 week before the shutdown, we are told that, okay, just stop now and no more run this year. So maybe if we had a little more chance, we could get a little bit higher. But anyway, this is what we achieved. And the data size we accumulated until now for Belle II is 400 inverse femtometer. And in case of Belle, we accumulated 1,000 inverse femtometer. 11 years of operation. This one is with 3 years operation for Belle II. So in that sense, it's higher, but the luminosity is higher, but this is not enough. We only have half of it. So I think we really need more data in the coming operation.
Instead, some more, this is a slide
Yes. This is basically similar to Barbara experiment. Okay, just a few words. I'm not an expert on accelerators. I cannot explain well, maybe, but this is a SuperKEKB. No. So as I said, we produce we generally make electrons here and accelerators here, and the electron goes inside this circuit. And for positons, we have some new positon target here, positon source here, and we produce positons. So basically, we inject the electron inside some target, then with kind of pair production, we produce a lot of electrons and positons, and we only collect positons. And then this positron is sent to this damping, newly produced damping. So at the time of KEKB, we didn't have this. But this one is to make low emitters need for positons. So, just to make a better quality positons. And then positons go inside being again and the circulator. If you have inside tunnel like this focus. Okay, and one key thing is SuperKEKB is called nano beam speed. So in order to achieve high luminosity, what we do is we basically squeeze the beam as much as possible. And well, at the time of KEKB, it's already very small. The size of beam is something like 1 micron times 100 the cross section. And but now it's something like more than 50 nanometers. So it's very small size. Hello, how about now? Looks normal.
We can hear.
Is it okay?
Yeah.
I don't really hear.
Yeah, now it is okay.
黄老师，您在线上能听得清楚吗？
现在能听清楚了，刚才突然断了一下，几秒钟。刚才突然断了一下，现在好了。
Okay, in my just one. In my side, I think this one was muted.
Anybody online can hear it clearly?
Yeah, 小龙 ，Yeah, we can hear.
Okay. Okay, then I switch to my PC for mic. Okay, just a moment. Okay, so let me summarize in one page about the year 2022 operation. So at that time, we were still affected by COVID, and the operation, was done by basically only local members. And partially we adopted remote, for example, remote shift, or remote people, of course, helped operation, but basically nobody could come to KK from abroad, and only foreign people, some of foreign people could come only in June 2022. It's the last month of the operation. But anyway, and as I said, increasing electricity price in Japan and in many of the world is a big problem. And I mean, originally we had a plan to have autumn run in 2022, but that was cancelled. And as I said, last week of June, this operation was suddenly stopped. I mean, cancelled. Okay, and in the operation, large beam background was quite a big issue. And okay, so you see, this is peak luminosity that's increasing and finally got 4.7. And but okay, at the same time we increase beam current. And but if you see this beam background, this top MCP rate, this is basically correspond to background rate, and this is also quite increasing. And this increase is much more than this increase of peak luminosity. So when we want to get high luminosity background, suddenly, not suddenly, but I mean, increase quite a lot. And also, this is one big issue because this top MCP PMT has a problem. I mean, have an issue on lifetime. And if we have too much accumulated charge, it's going to, I mean, it dies. So we want to limit this MCP PMT rate to a certain level. And this dot some limit we impose. And so this is one thing we cannot go higher beam current. And another thing, higher beam current, higher luminosity. And another thing is, okay, so trigger rate is also reached to quite how say high level, 13 kilohertz. So our Belle II in design, the max trigger rate is 13 kilohertz. But we reached 13. Sorry, and now but 30 is design, but now we can only accept until 10 kilo and 10 kilohertz. But actually, it reached at some point it's 13 kilohertz, and this is also already getting an issue. And well, but the biggest problem is we often see some sudden beam loss, and when we operated with higher beam current, and suddenly beam loss happened. I think I put together the page. Next, I'll talk a little bit next page. But suddenly, but this is very dangerous because sudden beam loss may destroy detector or some collimator or some other parts component of accelerator. So we couldn't understand this the reason. So for safe operation, we somehow didn't try higher than this, higher current than this one. And this one prevents the increase of the beam and also prevents higher luminosity. So basically, I mean, a few years ago, this top MCP was limiting the luminosity, but now this dangerous situation, sudden beam loss is kind of things we need to understand to get higher luminosity. And okay, so somehow this is. So during LS1, one thing we want to do is this understanding of this beam issue and also get more robust. So during Long Shutdown 1, LS1, we install kind of new robust collimator and upgrade the beam about loss monitor system for safe operation and to avoid this kind of sudden beam loss. So this is kind of some capture of some sudden beam loss. So this is beam current, and you see this this is only 60 microseconds. And this is 2 turn means so 10 microseconds is the cycle when this one beam turn around this 3 kilometer accelerator. And you see, I mean, up to here everything is okay. But suddenly this beam orbit became unstable. And also something is wrong, but around this 2 turns, suddenly this beam are lost. And finally beam abort happened. And then the beam are scattered somewhere and if we are unlucky, it destroys the detector or collimator. So now, I mean, so we have some observation or some, how to say, guess why this happens. So we are now, I mean, doing a kind of countermeasure. So we do some kind of upgrade, but we don't really know what happened after LS1. So we will carefully take, watch this situation. And if the problem is solved, then we can go higher current on higher limits. There are a few more upgrades of SuperKEKB to improve injections or some shielding of final focusing magnet, etc. Okay, then for the Belle II side, as I said, what we do this time is installation of second layer PXD. It's like this. This is already arrived at KK and already installed. Now we are closing. But in order to install this second layer, we first need to uninstall all the vertex detector and silicon detector, and then install in the lab, and then reinstall. And this is quite a huge work, but it's already done. And now we are doing some kind of commissioning, and we will close the detector soon, maybe in September or October, and then we reach at the end of this year. And in addition to this work, we replace this MCPM top detector, which I said this we have issue of lifetime, and some of them are already dying, so we replaced and the upgrade of CDC electrode. So okay, so maybe I spent too much time on this one, but anyway, then too we are doing quite a lot of. So we have really a lot of physics we can do, and this is we call it intensity frontier, and we study new physics with precise measurement. But in addition, we can do a lot of measurement for the property of D or search for new hadron or something like this, spectroscopy. And okay, just I introduce very quickly one new result. This presented at Lepton Photon 2 months ago, so maybe 1 month ago. And this is a measurement, new measurement of RD. So you may know, and if you attend this CPC conference, this is already given many times, and this is some kind of anomaly. We see something like 3 sigma difference between the standard model prediction and the this measurement for this the value called RD or RD star. This is a ratio of B to DL mu and B to D tau mu. And okay. And okay, so this is not penguin diagram, actually, this tree diagram, but maybe there might be some contribution of new particle physics, like leptoclones. And recently, new Belle II give a new measurement using 189 inverse 21 data, which is something like half of the available data. And when we do this analysis, what we do, we utilize that at E plus E minus collision, only 2 B mesons are produced, no other particle in addition. So when epsilon 4s decays to 2B, we tag 1B using some hadron to decay. And we look at the other, the rest of events should come from signal. This one is only, we have only tau, but in our, in this RD star, we have also D star or D. But anyway, so then what we say, we have a neutrino from this B, but we can say, if there is no other particle at all, then we can consider that this event is a series. So we detect D star and tau, and we don't see anything else. Then this means this decay is B to D star tau mu. We need, yeah. So we use this way, and we can. It's a very one of the, how to say, modes that which B factory has advantage in measurement. I don't go into the detail, but
the signature, main signature of this signal is, as I said, no accelerator darkmatter. But okay, then this most right-hand side plot is accelerator, and this red part is the signal, and the other part are backward. But anyway, this RD star is measured with Belle II, and well, with some rather better precision compared to Belle at the, if we compare the same sample size. And well, you see this left bottom plot. This is a new RD star and RD measurement, and this new RD measurement is bound on this side, which is not very small, but it's small compared to our luminosity. And if we have more data, this can be shrink. So I think it's good that we have first result of this kind of important analysis. And okay, so as I said, we resumed the operation at the end of 2023, and so to get more results, we really need increase luminosity and collect more data than Belle, as a first. But we also, many analyses are going on using the data up to LS1, so you can watch what we will have. And next week at EPS, there will be a new result on B2K new. So probably, please keep watching. Maybe it's a secret, I didn't tell it, but we will have, so probably we will have new result on B2K. Okay, then let me say about, let me talk a little bit on this dark matter, because recently I'm involved with this one. So that, as you know, dark matter cannot be explained within the standard model, and we only know that the dark matter is not a standard model part. And so we don't know about dark matters, but well, there is one hypothesis which was convinced for a long time, and I think this is still kind of one of the important hypothesis is this WIMP impulse. So this in this hypothesis, this is also called WIMP miracle, but in this hypothesis we should have some heavy particles. Heavy here means 10. Sorry, I think this is wrong. 10 to 1,000 dB. So order of 10 to 1,000. So something like a few 10 dB to a few thousand, a few dB. This particle that interact with similar strength as a WIMP interaction. This is a WIMP. And what's good is, if I assume that this large number of WIMP dark matter, this is a candidate of dark matter, and if we assume that the large number of WIMP dark matters were produced at the early universe, and then they decrease due to annihilation with this interaction, then the present abundance, the remaining amount of dark matter is consistent with the observation. So this is one good thing. And from the viewpoint of particle physics, we really want this new particle at this mass length, like TeV or 100 GeV. This is actually necessary to solve the hierarchy problem of the standard model. So from actually, when LHC started, most people convinced that there should be something at this region. So this is quite desirable in the particle physics. And also this mass range is very convenient for experiment because also because with experiment, because this can reach with LHC, and also there are many underground experiments that are trying to measure dark matter, observe dark matter, but with this assumption, they come in the reasonably good range of interaction. So, so I think this was many people search for this WIMP dark matter, and it's still, of course, it's still searched, but unfortunately, it's not observed yet. So that's the situation. So I think maybe we need some more idea. Not nothing. So I think we need to change our mind so that we should search for dark matter in wider range of these various techniques. And so actually this is some kind of granting aid and some project that I'm involved in Japan. And I got some money and some people are working on this one. But anyway, so not only, so people are looking, most of us were looking only focus on this one, but actually there is still much probability. And this black region is not adapted. So it's Japanese, but I think you can understand. It may be just a wave, or it's maybe even some big, some composite part, or very big size, like as big as stars. So, but okay, with accelerator, what we can search is only this region. So, but one thing, this WIMP region is can be done only by LHC, or maybe future CPC or ILC or future E plus E minus collider. But for this region, we can do with E plus E minus collider available, that's like Belle II. And so we can search for dark matter below 10 GeV. And the good thing is we have very clean environment. And typically, this kind of dark matter particles are kind of missing energy. So we look for this particle with invisible returns. So this is very good place. So people are, I'll say, many people are, at least many Belle II members, not many, but some of Belle II members, and some people are quite interested in the study this dark matter with Belle II. And okay, in terms of this kind of so this kind of dark matter, the existence of dark matter particle is not really a very new idea. But in the standard model, we can have some kind of extension to other hidden sector. And in this case, this standard model particle, this is called dark sector, but in this case, the standard model particles have interaction with some called mediator. And in another side, we have a world of dark matter. So maybe there are many particles in these dark matters, or dark sectors, and there are some other interaction. But there are some mediators. This mediator means it has an interaction to both sides of this standard model particle and dark matter. And depending on the property of this mediators, we have basically only four kinds of mediators, and depending on the property, like scalar or pseudo scalar. And depending on these mediators, the name they have different names. So maybe you have dark heats or action-like particles or dark photon. So another dark boson. And this sterile neutrino, this is also possible, but this is outside of the reach of the experiment. And okay, and in some model or some cell, in some case, these particles, these, for example, dark photon or G1, this may explain this the discrepancy of G minus 2 muon between theory and experiment. So that's also another kind of interest. And in case of Belle II, what's typical process? So as I said, we can search only up to 10 GeV. So we are looking for light dark matter. And the typical process is we have the E plus E minus collide and some standard model particles are collide. And in addition, maybe some mediator. This is important. So this is just one example. The E plus E minus collide and the mu plus mu minus the process associated with this some deep line. And this one later goes to some dark matter. This can see can happen. And okay, so some of these processes have not been searched in Babel or Bell experiment before because they need a special trigger setting. And so in that sense, this may be searched with initial velocity there. So the right-hand side is just a kind of some typical event. Okay. Another example of such at Belle II, I introduced just one. So this is the same process, E plus E minus goes to mu plus E minus D prime. And this D prime one, dark matter cannot be directly detected at Belle II. So they are missing, but we know the initial beam energy and also this mu of momentum. Then we can calculate the recoiled mass, and we can basically look for this D prime. And if we have some D prime, it makes a peak to recoil mass. And in this case, there are of course there are some background due from standard model process like E plus E minus, because we are looking for E plus E minus mu plus E minus was missing. But okay, for example, E plus E minus mu plus E minus gamma, and if we fail to detect gamma, then this looks like similar. So we see this result. But we don't see any peak, so this means there are no hint of signal. And by the way, this measurement mostly excluded this the interpretation that D prime is the reason of this G minus to this discrepancy. And okay, I just show you one result, but basically no hint of signal at all for other measurements also. Okay, and so just a few about trigger, and so we need to trigger to initiate data acquisition, and only trigger events are recorded. But the main purpose of Belle II is study of B method or other term or tau. And in such event, we have quite a lot of particles, not quite a lot, but something like 10 particles. So it's basically easy to trigger. And actually, the trigger efficiency for BB is almost 100% because we have very high priority for highest priority and with high efficiency. And okay, but this is rather easy because we have many charges. But other events like very few track, like a 2-photon event, this is also used for analysis, or some dark matter event. They are basically low multiplicity event. We only have 2 or 3 tracks. They have less priority, and they are triggered as far as the bandwidth is allowed. And as I said, we are already sometimes hitting the maximum. So maybe we need to start thinking about reducing the bandwidth. Then we need somehow give up this trigger for low multiplicity index. So we don't want to kill these triggers. So the important thing is to suppress triggers from beam background and keep high efficiency for low multiplicity events, so for dark event. Okay, so then I have a few slides, but maybe I'd like to skip a little bit detail. So we have some trigger logic, and the main part is trigger from collecting and trigger from calorie data. So we want to increase the trigger. We want to improve the triggers for this part. And so what we are doing, this our team is doing, is trying to implement a little bit better trigger using our universal trigger. So this trigger logic is implemented in this UT board. I don't know if maybe you are using for KVM also. Maybe not for KVM, but KVM also uses this one. But okay, so the one we are ready to work with upgrade this small size unit, small logic size unit is remote in UT4 board. And yeah, we are already working on this. And I said we, but actually I'm not working on this kind of Superman, Yun-san, who is now in KK electronics group, but he somehow did this kind of work within our project. And he also developed some as a new triggers, but upgrade some trigger, but let me skip this one because I already took a little too long. Okay, so the basic dark matter search mode. Dark matter search should be this mode, E plus E minus code gamma invisible. So basically it produces just one photon, like initial state radiation, and the rest goes in this invisible. And okay, so this one we have already in the final state we have only photon, photon plus nothing. So what we do is we measure, we take event, we just have only one photon and look at the recoil mass and find a bump of this dark particles, actually dark photon. And okay, so this one need, but I mean, usually, I mean, if we, it's difficult to detect trigger event with just one photon. So we need special kind of special single photon trigger to collect such event. And Bell didn't have this trigger, so Bell has no result. And in Bell, actually many people quite intensively work this one, but now the problem looks we have quite a high background, beam background, and background is higher than expected. And so we are still struggling with how to understand this distribution coming from data. And okay, so if we have to continue this measurement, in future, I think we also need to improve triggers, and that's one thing we need to do. Okay, and this is, there are actually many analyses that can be done. And one of the search, actually, I'm already involved with search for heavy QCD action. So, we made that the action is, introduced to solve this strong CP problem. And but with this, this QCD action, the mass is quite, range is quite limited. And if action is a dark matter, this much lower. But but with some extension of this scenario, we can have this some scenario that this action is much more heavier. This one solves the strong CP problem, but doesn't directly solve dark matter the universe. But still, we are looking for this. We can look for this kind of thing. And well, in this case, this kind of signal is can be searched like B plus KA, and A goes to hadrons. This A is what we are looking for, and this branch fraction is given like this. And okay, and we are working for this one, and now we know that this kind of mode can be searched with Bell II with and improve the limit, and we have some kind of optimization of selection criteria. But unfortunately, this analysis has stuck a little bit because first postdocs who are working for this one somehow we are looking for new postdocs. But anyway, we can do this kind of measurement. So we can have it. I think we can get result in a year scale. And another analysis, this is from maybe you know Kindo-san, he's from KLM group. He was doing and still continuing with. So this analysis. So we can look for this dark photon using the charm decay, D star to D0 photon. And in this case, this photon can be converted to dark photon, but because of the mass difference of D star and D, the sensitive region is from 10 to 100 MeV. And actually, at energy, at mass of 17 MeV, there is one kind of anomaly found in atmospheric experiment and internal pair creation beryllium. And so this may be just a kind of explained by standard model, maybe some dark matter. So I think this can be confirmed or checked by these factors. And in Texas, there are some other people who are trying to do this with other methods, but actually Kinderson is trying with instantly gate. Unfortunately, with data only, the sensitivity is not enough to basically cut confirm this X17. And well, but anyway, we hope to get this result soon. Okay. Maybe I skip. We have another. So, in addition to this, there are really many search for dark sector particles in Belle or Belle II. And well, some of them are quite already taken by somebody, but I think there are still a few left. So maybe if you are interested, you can join. But in general, it has import has it's not. It has some difficulty in many cases. Okay. Okay, so it's already. So I think Belle II was Belle II will return from this end of this year, and I hope we collect more remains, and we can get more results. And we have many dark matter studies with Belle II and Belle. But this most important one is takes time, and in general, we need to improve the trigger as the luminosity background increase from now. So I think we need both effort in doing analysis, but also improve triggers so that we can continue this kind of dark matter study in future. Okay, thank you very much.
So next, let's go to the questions. Let's start from online. Any question from online? Hello?
Hello? Hello, can you
Any
hear me?
question from online?
Hello?
Yeah.
Yeah,
Somebody's
I
asking.
have a question on page 29.
Okay, just 29. Yes.
Yes. I just wondering, how do you ensure the photon is from initial state?
So this is not really necessary. This photon can come anywhere, but okay. In this diagram, the only place is here. And what we need to know is we need to ensure that E plus, this comes really from one event, E plus E minus, and we do not have anything else. That we need to ensure.
If the photon is not from initial state, then the physics model should be different. So we cannot extract the epsilon from this physics model.
Right, but in any case, this even if we found this gamma plus invisible mode, we cannot say it's coming from this. This model. So we cannot identify this model. But if we see some bump, at least we can say we can have this kind some dark matter particle. That some dark particle exists with this mass in this mode. So to really identify the model, I think that's the next step.
Okay, now you mean this diagram is one of the possible diagram?
Yes.
Okay, thank you. And I have another question. I notice all the searchings are model dependent. Can we perform model independent searching?
That's I think not. I mean, to some extent, all the search become I say model dependent. But for example, I mean, so what we can do is we can find this kind. We can try to find. We search this mode, and we see no event or whatever, or we find some bump, and then the interpretation can be. I mean, then anyway, model dependent. So I think it's not so. I think it's the same for any searching with accelerator. It's always, to some extent, model dependent.
Okay, thank you very much.
Thank you, Lingang. And any other question from online? If not, so question offline. I encourage the student to ask questions.
You can ask the easy question for operation or whatever.
To go to page 16, 17.
This one?
Yeah, that is yeah, the data sample uses less than 200 restaurant around.
Right.
So why not use all the person?
I think originally this analysis was, it was supposed to, go out much earlier, and it takes time, I think. And this is really complex. I mean, so we need to target one side, and this, in general, this is really hard to say. We need a careful check and some kind of calibration of because this, for example, the efficiency of this herbicide efficiency really depends on how much, what's the fraction of each BDK for each hadron. So this really takes kind of time.
Okay, I see. The page 19 regarding the wind.
Yeah.
Did you pay attention to the lifetime of winds? Is there any prediction on the lifetime? Really bigger long particle?
I think that's okay. So I think there is when we just say WIMP, we cannot say anything, and because
it's a weak interaction.
Yeah. Okay. So because what we know, basically what we are looking at the accelerator is this mediator part. But in some case, these are dark matter in the universe. But in some case, these are just a mediator and decays, and later, there are other stable particles in this. So I'm not sure, but I don't think we can limit with this one. So we have.
I was thinking about at the beginning of the weak interaction.
Yeah.
It looks like many particles form.
Yeah.
Always has long time.
Yeah.
And long lifetime. Even like a PDK.
Yes.
The dimension also has a long life.
Yeah.
So maybe a wind has a much longer lifetime.
So I think it's not good. I don't have a slide, but I think there are we already have many presentations in this workshop, PC workshop also, but I think there are many efforts to find a long life pattern. And in Bell, we have a search for LLP and long-lived particle. One result we have some from BDK, but I think LHC people are quite considering a kind of a lot of effort. And also we can put the detector, quite far detector. Yeah. and like a phasor experiment near Atlas. Well, I think in ILC or C, I think in CPC also, they are considering as a power detectors. I don't know for CPC.
Actually, that was my idea.
Okay, yeah. Good. That's good. I think see also now, trying to get an idea of this power detector because it's okay. So in LC case, we can do also this beam down experiment. Anyway, because if we want to make a new power detector later, it costs much. It's difficult, but at the time of construction, maybe we can also make a power detector with small additional cost. So I think there is some proposal or studies going on.
Okay. Good idea. In the page number 25,
yeah.
Regarding the trigger,
yeah.
Especially current trigger, do you know anything about the state of current trigger? I know there was a postdoc of Tech.
Yeah.
He worked on it for many years. What did he achieve?
So I don't have a
Looking at the next one.
No, that's good.
I mean, next, right?
Next one. Yeah, the trigger has the several times. How are you doing it?
How the performance?
I don't know.
Okay.
But actually, KLM trigger is, very important. Maybe not only for this low multiplicity, but also for other, like, because it can basically trigger any event with mu, and that's quite important because then many low multiplicity process can be saved at least for mu. Okay, so it's very important.
Yeah, as I remember at the beginning of the C experiment, that trigger many folks that's a focus on mu. Okay. So any other questions?
Yes.
Yeah.
You mentioned when the beam goes, it will destroy some defect.
So so usually, okay, so when beam are circulating, of course, some beam, small part of beam are always lost, and this become a radiation anywhere. But in the normal operation, not written here, but when we want to throw away beam, there is another special beam dump part, and beam goes to this beam dump and then throw away. But beam loss in very short time means this beam goes somewhere, hit somewhere, and basically lost. So I think that's very dangerous. So and I don't know if it's hit in one place or, but anyway, quite very high energy of this beam. Large part of the energy of beam goes to some unexpected part. Yeah, that's very dangerous. And actually, in reality, before LS1, many times this collimator is something like to cut out the outer part of the beam. So yeah. And but many collimators are broken. Not many, but a few collimators are broken. And this is really a big problem. If it's get broken, then we either open the detect. This takes a few months, and or in some cases we cannot increase the beam because of the broken collimators. That's a very problem.
I understand actually. By now, the strategy for dark matter detection is only identify the missed particle, the missed
So I think that's most part of the analysis is search for some missed particle, but I don't think most is not really. Large part of the analysis is looking for some missing because of this dark matter. But in some model, they predict that this dark matter further decays, and again standard model for particles are produced. In such a case, we try to find a band with some.
what is the difference the action and the acceleration?
So action, in the narrow meaning, action is this QCD, so QCD action. So it's solve strong CP problem. But I mean, basically, I mean, you can propose any other pseudo-scalar particles that has interaction between. So they are not really actions that solve this CP problem, but have the same properties. That's action, like.
Okay. I mean, the action is mainly coming from this velocity.
Yeah.
It's kind of from the physics point.
Yes.
But action like particle,
right?
It's something just
yes.
Invented some.
Yes.
So
it's right.
From very strong physics motivation.
No, how to say, no direct. In my understanding, so action like particle doesn't have no direct motivation, but it's allowed within standard. And in some sense, it's allowed within standard. It can couple. I mean, it doesn't. How to say, it's not inconsistent with already existing measurement, and also doesn't destroy the structure of standard model. That's an action. Likewise. So it's a less motive. I agree.
No. Uncertainty is very
yeah.
So
yes.
It's difficult to
Yeah.
cover all the
Yes.
Okay, 32.
Also King.
Yes, saya di master working design. It looks like some event around your.
So sorry, this is a Monte Carlo. This one. So this red one is just has a his signal.
Yeah, but it really looks like some pins.
Yeah. And if you really find something like this, then it might be. But this is Monte Carlo.
Okay. Another question actually about the detector.
Yes.
Originally, there's a reflection of the MCP-PMT, but they are very expensive.
Which one are you talking
about? I mean the MCP-PMT.
MCP-PMT, yes.
It looks like they are very expensive.
Yeah, that's very expensive, and but I think anyway, without that MCP, we cannot continue. So partially Nagoya University is very deep choice.
Okay.
But it's really expensive. But okay. So it's it's not how to say. Now we have some. We knew this problem from before, so we make a spare, quite a lot of spare. And but this during the lesson, I think we use most of the what we have. So I think in future it's a problem. So we need to find more budget and fine. And we need to really estimate when we need to replace them, and we need to also prepare more spares. That's a little bit big problem.
Okay. So if no more questions, let's just thank you.
Thank you very much.
Okay, we can end the seminar.
Yes. Okay, so I will suggest this minute.